Which lecture was isothermal PFRs and PBRs? Actually, I've got them here. Let's see. 11 was our introduction to flow. 12, yes, up to 12. So if you encounter something on lecture 13 or afterwards, that is not on the exam, because lecture 13 was our derivation of the energy balance for a flow reactor. Everything prior to that is gain. So that does include the pressure effects, right? Because those aren't an energy problem that we're dealing with. You are not going to have to solve the Ergun equation on the exam. And I think that's all I wanted to write about the exam, other than it's on Monday.
Professor?
Yes?
Will it include material from exam 1?
Sorry?
Will it include material from exam 1?
Yes. So it will include energy balances on batch reactors. So no energy balance on flow, but everything up to that point, including energy balance on batch reactors, is gain. Let's see, I was going to announce something. Oh, if you didn't see the announcement that Jenna posted, she's going to reschedule her office hours, right, on Monday. So there'll be another announcement about that. And then before we get started on our topics for today, which I'll briefly mention the key ideas when I get to it, is what we're going to do in week 10. So I'm going to modify the syllabus a little bit on week 10. The topics that we were going to cover in week 10 were things that I was generally interested in. Week 10 is not going to be stuff that shows up on the final. It's to give you an idea of what can we use chemical reaction engineering for, or where does it show up when we're not inside of a classroom somewhere. So, we are, oh, what happened? Okay, we're going to have to do the unplug thing. It's all right, it's still recording. We're done with plug flow and packed bed reactors. There are no more topics in there, so we're starting our last topic in terms of what kind of reactors. Those reactors are called continuous stirred tank reactors. And so today, the key ideas that we're after are twofold. One of them is an equation. So if we have something like a volume, we're going to find out that this is pretty simply related to some flow rates as something like this. The other thing that we're going to introduce is a new term that we haven't heard before because we've never needed it. So the new term is the well-stirred approximation. The content for this in Fogler, if you want to find out where this stuff is in the book, where did I write it down? There it is 1.4 gives you a general intro, 4.3 goes into it in a little bit more details. Oops, there was supposed to be a 2.3 in there. Sorry, those aren't organized. And if you're looking at the homework, just from today, we should be good with 6.1, 6.2, and 6.4. Notice what doesn't show up on our key ideas. There are no differential equations. We don't have differential equations for stirred tank reactors, which does introduce some kind of odd things in our equations, more in the energy balance than the material balance. But that's where we're headed. It's a simple equation like that, and we want to examine what this well-stirred approximation means. So what's a CSTR? The type of reactor that we're talking about is what's called a continuous... Wow, that pen is kind of zonking out today. Continuous stirred tank reactor. And that name sort of gives you all the information that you need. The abbreviation CSTR comes from those four. Just as a nomenclature point, some people like to call this a continuously stirred tank reactor. A continuously stirred tank reactor is a batch reactor. If you just have a tank and you continuously stir it, that doesn't say anything about flow going in or out. So the choice of the word continuous means that you don't have a batch reactor, you have a flow reactor. It's continuous in the sense that material is coming in and material is going out. So you will hear occasionally people say continuously stirred tank reactor. Strictly speaking, it's continuous, but everybody kind of knows what you mean when you say CSTR or continuously stirred tank reactor. The diagram that we typically use for this, actually, unlike the plug flow reactors look like that diagram. The reactors really do kind of look like this. If you vote for the bioreactor, I can steal the bioreactor from our lab and bring it in so that you can see what it looks like. Looks like a tank that has continuous flow going in and out. There's usually a mixer that sits inside here, hence the term continuously stirred. In order to get it to work right, you have to add those little marks that indicate the stirrer is working. There is some flow coming in at some volumetric flow rate V, which looks suspiciously like a nu, but I'm just going to leave it because we're going to have to deal with another V. And there's some coming out at some other flow rate V, and the volume that we're dealing with is capital V. Typically, stirred tank reactors are dealing with liquids. Not all the times, but most of the time CSTR has liquid inside of it. One of your homework problems has a gas inside it, which is a little bit weird, but it's not impossible. You're kind of blurring the lines between a plug flow reactor and a CSTR if you put a gas in there, but it's possible. Some people classify them as CSTRs. The other big thing that's going to be our friend is that they are always going to be steady state. If they're not steady state, then you're taking 120. CENG 120 deals with systems that aren't at steady state, usually in terms of a control problem, but you have to derive the expressions for material balances based on not operating at steady state. Because we typically have these two assumptions, if you do have a liquid, then you have that the volumetric flow rate going out is the same as the volumetric flow rate going in. Right, and that leads to that simplification that we've seen previously, which is if you ever need to know the concentration of stuff coming out, that's the molar flow rate of that stuff coming out divided by whatever the volumetric flow rate is of that stuff coming out. If it's a liquid. Most of the time with CSTR, yeah, it's a liquid. Not a bad assumption. And the third thing that we get, which is usually more useful in a continuously stirred tank reactor as an additional parameter that you see thrown around a lot, is a parameter that we already saw, which is your residence time tau, which has the same derivation that we already saw, which is the volume of the reactor divided by the volumetric flow of the reactor. So just like before, that residence time says on average, if I'm a little packet of molecules and I enter that reactor, about how long do I spend inside that reactor? On average. There's a distribution, it's actually called a residence time distribution that can tell you what's happening inside your reactor. So tau is not always constant, but nevertheless, we define tau as a constant. As we'll see when we get to the energy balance, if you want to change the temperature of the reactor, you just put a jacket around it in the same way that we had sketched for a batch reactor, which I will sketch in tomorrow's or Monday's lecture when we talk about energy balances. The first thing that we need is a material balance. So the control volume that we're going to talk about is the volume of liquid that is inside our reactor. So I'm going to highlight that in the fuchsia pink purple color that nobody knows. Control volume. And our material balance on a control volume like that, it's the same one we know and love at this point. Accumulation is in minus out plus generation. Again, the consumption term is sitting inside there. It can be consumption is negative generation, so we don't really worry about that. It is always going to be at steady state, so we don't have to worry about that. So we end up with 0. The amount of stuff coming in, if we talk about per mole of A, is FA naught. The amount of stuff coming out is FA. The rate of generation or consumption is RA times the volume of the tank. Right, RA here is always RA. It's always on a per volume basis. We never have catalysts inside here. We don't pack one of these full of catalysts. So RA would have units of what? Moles of such and such reactive per volume per time. And if you multiply that by a volume, you get a moles per time. That's it. It's an analytical expression that relates all of those because the volume is constant and we need to calculate the flow coming out, most likely. The rate law A is expressed typically for elementary rates, just like we've always seen it. So one way that you see this rearranged is that the volume of your reactor is equal to FA naught minus FA over minus RA. And that's the whole material balance. This is what's so nice about CSTRs. This is a material balance on a CSTR. There are no differential equations to solve. There are no initial conditions to worry about. There's no use of ODE 45. Dump the equations in here and you solve it. The only thing that can become tricky in this is, depending on how complicated your expression for RA is, you might not be able to isolate a variable like FA. Right? You might have to solve this thing iteratively, which is to say dump it in your calculator or something like that. So it's not that you can solve them all analytically, but most of them can be solved analytically. Because this is a flow reactor, our definition of conversion is just like what we saw before for the other flow reactors, which is FA naught minus FA over FA naught. That leads to the following variation on the material balance, which is that the volume of our reactor can also be calculated as FA naught times XA over minus RA. That's an equivalent form for a material balance on a CSTR, typically restricted to one reaction. You don't have to write these in terms of A. If you need any of the flow rates of anything else, you can rewrite the volumetric term that we saw before. So generally the volume is going to be equal to F of any species I minus F sub I over minus R sub I, whatever the rate is for that particular reaction. So we've written them all here in terms of A, but it works regardless of which one it is. If you're worried about the signs between those, just work through the signs and use a little bit of intuition. If I didn't feed anything, it must have been positive. So that number will end up being, should end up being positive. Yeah. That's it, with the exception of how do we figure out what this term is? What is R sub I, or more generally, what is R sub A? The reason that it can be a little bit tricky to figure that out is because we have a tank. It's filled up with liquid. Presumably the concentration of Ca over here at the inlet is larger than the concentration of Ca at the outlet. Otherwise you didn't react anything most of the time, which means there's probably a gradient inside the system, right? Initially, if you're here, if we zoom in on this part right at the inlet to this, if we assume that Ca is, I don't know, purple, there's probably a lot of Ca over here. right? But if you look at the outlet over here, this is what it looks like. They appear as dots if you zoom in. You don't have as much CA. Typically, that means there's a gradient somewhere inside here, right? You're starting off at high concentration, you're going to low concentration. We don't really, that means also that the rate up here, R sub A, is going to be higher than the rate down here. So depending on where you look inside the reactor, the rate is different. If you really had to account for that rate difference, this would be a pretty challenging problem. The reason it would be pretty challenging is because somebody came along and put a stirrer in here. Right? This thing is paddling around, mixing everything up, so now you have some pretty complicated fluid dynamics going on in there, which are all changing typically in time because that thing is stirring around. To avoid all of these problems, we use what's called the well-stirred approximation, which it comes up in a lot of different topics beyond just chemical reactions. So the well-stirred, you know, about half of my words look like I'm a serial killer and the other half look like I'm an okay guy. Like those two R's on well-stirred. The well-stirred approximation is the following. The concentration of A, or really, let's not say A, let's not limit it to A. The concentration of anything, I, within the reactor is always going to be assumed to be equal to the concentration of I at the outlet. This is the well-stirred approximation, which means if we know what's going on at the outlet, then we're going to assume that we know what's going on inside the reactor. So we're going to assume that all of the gradients inside there got mixed up enough so that the internal concentration of that tank is essentially uniform everywhere. That's the well-stirred approximation. If it's uniform everywhere, it doesn't matter where my outlet is coming out, I'm going to grab the same concentration as whatever was inside. So this well-stirred approximation lets us relate what's going on inside the reactor to what we can measure, which is what's coming out of the reactor. So when you see a rate law such as R sub I, this is going to be a function of C sub I at the outlet, which means that we write it in the normal way, which is some function of C sub I. Right? Previously, we've never bothered with the distinction between the concentration of species I inside the reactor and the species of I coming out of the reactor. Because everywhere species I was, we were figuring out what was happening inside the reactor. Now we don't really know what's happening inside the reactor. We're just lumping it all together and saying, well, it's well mixed. Which is not a terrible approximation if you imagined a bucket and you're slowly adding dye to it. If you mix that bucket up fast enough, as soon as that little droplet of dye hits, it gets spread out pretty well. It's not a terrible approximation. We use it with mixing stuff, like I just mentioned. We use it with reactors. We use it with heat transfer. It's not a bad approximation. It tends to work pretty well as long as you're mixing things up to an appropriate degree. Any questions on well-stirred approximation? Not that bad, right? There's no real math. It makes our math so much easier. The only variation, we have now covered all of the material balances on continuous stirred tank reactors. There's nothing more to talk about other than examples. The extension to multiple reactions follows exactly the same rules as we saw before. So anytime that you saw an R sub I, that is actually going to be equal to the sum of the rates of that species participating in all J reactions. And that's it. There's no change to the material balance. There was no change to the material balance in any of the other reactors either. Right? The material balance just needs to add up all those rates, and then you're done. There's nothing else to add to it, which is kind of nice. It makes the CSTRs generally simpler than the plug flow or the packed bed, or certainly the time-dependent batch reactors, because there are never any differentials to solve. We're going to see on Wednesday, which I love this topic on Wednesday, you can get weird things because these equations don't always give you a unique solution. Sometimes you can have multiple solutions, and for once in our life, the multiple solutions are actually relevant. We can actually operate the thing at different steady states because the math tells us that we have multiple steady states. Most of the time we calculate more than one answer to something and we ignore part of it because it's negative or imaginary or has nothing to do with us. Here, those other solutions are actually reasonable. So we'll see that on Wednesday. We have to get to energy balances. But otherwise, the solution procedures for these are write down all the equations that you have, solve all the equations that you have. There's no differentials that you have to write. In some cases, there's no MATLAB you have to use, unless MATLAB is what you do in your own time to solve nonlinear equations. Your calculators can do that, Excel can do that, Wolfram Alpha can do that, and certainly MATLAB can do it. Does anybody use anything other than those? Maybe Google Sheets, they can do it.
Python?
Python can definitely do it. Can't think of any other common ones. Anyway, let's see an example. Actually, better yet, you do an example of what these kind of problems look like, the typical kind of information that we're given. So, for example, find the volume of a reactor, which, by the way, that'll be one of the topics that we get to in the design portion is how do I know which reactor to use? Usually we pick the ones that are smallest, right? If I can build a smaller reactor, then I typically save the company money. So this question of finding volume will come up again on, I think, the following Monday, or maybe actually next week. No, the following Monday. Find the volume required if I want to convert 90% of species A if the average residence time that I need is 1 minute or 10 minutes? 1 minute. So sometimes with CSTRs, they won't tell you what the flow rates are, or they won't tell you what the volumes are. They'll give you what the residence time is. But as we saw before, those three parameters, the volume, the volumetric flow rate, and the residence time, they're all directly related. So if you know any two, you know the third one. Tau just happens to be a way that some people specify what that third one is. So the figure that we're going to be worried about is a CSTR that looks like this. Some people, by the way, like to draw their CSTRs like this, putting their flow rates like that. It really doesn't matter how you choose to draw it. There's going to be 6 moles of A entering per second, and it's going to enter at a rate of, 6 moles of A and 50 moles of an inert per second. Again, make sure you put the mixer in there and add the little motion indicators. The reaction that's occurring is just a simple 2A goes to B with a rate constant K of 10 to the minus 2. We're going to assume the whole thing is elementary so that our units are liters per mole per second. And I think you needed one more piece of information. No, I believe that was all that you needed to know. I'm double checking to make sure that you're good. Yeah, no, I think that's all you need. So take a couple minutes here. Feel free to work in groups if you want, and see if you can figure out what kind of volume that we need for this. So the volume is an unknown. The rate is elementary according to what was written here. So R sub A is K, Ca squared.
Question?
Yeah.
So is just A in the inert? Is the inert, would we treat that as like a solvent?
Is just what inert?
Is the inert just a solvent?
Yes.
Okay.
this. For those of you just joining us with the podcast, these were our calculated values. We just spent, what was that, about 10 minutes trying to calculate this? So we're at least going to get to, well, I will tell you at this point that my answer is on that list.
240.
You got 240?
I got 240.
You got 240? We got another, so we've got now 3 240s. Did somebody else say 2.4?
I got 240.
Another one? Somebody else get 2.4?
I got 2.4 actually.
2.4? 2.4? Oh man, this number is going up. A lot of people getting 2.4. So let's just look first at how do we set this equation up, right? We always have to go back to the material balance, so the volume is going to be equal to something. Which version of the material balance do you prefer? The one with X or the one without X? With X, right? We were given X, so we might as well start off with that one. We start off with FA naught X over minus RA. Now we start substituting stuff. This is XA. Should we replace FA naught with anything? No, FA naught's good. We were given what FA naught is. We have to replace our rate law. So we would end up with KCA squared underneath FA naught XA. How can we rewrite CA? How can we rewrite CA in terms of conversion? CA naught 1 minus XA. Don't forget to square that because of our rate law. Who just forgot to square it? Yeah, I heard it. Over XA. So far we're okay. We just have to get rid of that CA naught term. CA naught is what? FA naught over V naught. V naught being our flow rate. But we're kind of stuck, right? We don't have a flow rate. What can we use instead? The residence time. Remember, our residence time, tau, is equal to V, the volume, over the volumetric flow rate. This is one of the oddities of CSTRs, is sometimes people prefer to talk about residence time because that's the average amount of time a little element sits inside there. That is less useful in plug flow and packed bed reactors because usually if you know how long the thing is and you know how fast it's coming in, you can figure out how long it stayed in there without too much effort. So it tends not to be particularly relevant. All of our differential equations are built in terms of W and V anyway, so tau doesn't come up very often. It does come up in a CSTR a little bit more because now if you don't have a residence time, you really have no idea how long that thing is sitting there inside the reactor. So it's just a convenient parameter that shows up occasionally. So if I rearrange that, then I will get tau FA naught over volume V. If I plug in both of those to my expression, I get V is equal to FA naught XA divided by K times quantity tau FA naught over volume times 1 minus XA, that whole thing squared. So while I've been blabbing on, has anybody rearranged that and gotten a new volume? 2.4. Right, so there was nothing fancy in here, but it is a little bit tricky. You got to keep track of where everything is going. But that's about the extent of what we would deal with in here. It can get a little bit more difficult if your rate term down here looks nasty. Right? Reversible reactions, that's not going to be pretty. Yeah? 1 minus 2x. Ooh, he's right, isn't it? It's a 2. Now everybody screwed it up. How could you make it a 1? right, we're out of time, so we can't go over it. But play with that and see what the 2 looks like. I don't know. If you put a 2 in there, what happens?